This is the logistic regression video on interpreting the model parameters. The data array for logistic regression looks identical to that for a continuous outcome, with the exception that the outcome is usually coded as 0 or 1. In particular, R executes exactly the same set of maneuvers when turning categorical predictors into indicator variables when coding interactions, and so forth. This slide illustrates that the right-hand side of the logistic regression model looks exactly like the models that we've already studied. The left-hand side is a transformation of the probability that the event will occur. Solving the previous equation for P yields the formula in this slide. Making this calculation is straightforward but tedious. Unfortunately, your software will do it for you. For continuous outcomes, the relationship between x and logit P is linear, whereas on the original scale, the plot of x versus the probability of response is sigmoid-shaped. For continuous outcomes, we went through an exercise demonstrating that the indicator variables really do work. If you'll recall, we plugged in the zeros and ones for each group, calculated the predicted values from the model, and noted that the beta coefficients represented the impact of comparing one group with another. The same exercise works for logistic regression, as illustrated in this slide. The only difference is that once the predicted values are obtained, you take the ratio of one prediction to the other. The demonstration requires noting that since the logit is the logarithm of the odds, exponentiating the logit yields the odds. The demonstration also requires remembering the few point properties of exponents. In any case, everything really does work, and it should be clear that when group has no impact, the value of beta is 0. Thus, the null value of beta is 0, and since e to the power of 0 equals 1, the null value of e to the power of beta is 1. Beta represents the log odds ratio, whereas e to the power of beta represents the odds ratio. You can go through the same set of calculations for continuous predictors, although we won't demonstrate that here. The most important implication is that the beta coefficient represents the impact of a one-unit difference in x, regardless of the value used as the reference, on the logit of the probability that the outcome event will occur. However, when you return to the original probability scale, this no longer holds true. In other words, the absolute difference of impact of a one difference in x on the probability the outcome will occur depends upon x. The most straightforward way to help your audience keep this straight is to report actual probability of outcome for various values of the predictors. Alternatively, you can report the entire logistic regression equation, including the intercept, which will allow your audience to do the same. If you get the outcome variable backwards, there's no real harm done. The p-values will be the same as before. The odds ratios will be exactly inverted. Indeed, the fact that the odds ratio is in the wrong direction will probably clue you into the fact that something's wrong. As with continuous outcomes, the interpretation of the regression coefficient is that it represents the impact of a one-unit difference in the predictors, with all the other predictors held constant. We won't bother with the demonstration. Having gone through the exercise of working through what odds ratios mean, you might still quite reasonably note that they lead to a model that seems rather complicated, and ask why statisticians seem to want to embrace this complexity. There are three reasons listed on the slide, of which the first two aren't unique to a logistic function. The third reason, pertaining to case control studies, is the one why logistic regression has found such a prominent place in medicine. The result, and an amazing one at that, begins by noting that case control studies measure the opposite of what you really like to know. These designs subdivide patients into healthy versus diseased and ask whether these two groups differ according to the exposure to a risk factor. In other words, what you have is the ability to work backwards from disease to exposure. But what you really want is to work forward from exposure to disease. That is to say that the exposure ultimately causes the disease. The amazing result is that the odds ratio of exposure given disease equals the odds ratio of disease given exposure, thus allowing you to interpret the data prospectively, even though it was collected retrospectively. Once the odds ratio enters the picture, the logistic regression model naturally follows. This slide contains a symbolic version of the same argument.